All right, so today's lecture is about the engineering design process. And our learning objectives for this module are to distinguish the work that's done by different engineering disciplines, describe the purpose of each of the individual steps of the engineering design process, apply the first and second step of this design process, which is problem definition and identifying criteria and constraints, and finally to assess the level of community participation in a project using the typologies for community-based participatory design. So let's start with the different engineering disciplines. What do engineers do? In short, the answer to that question is that engineers solve problems, right? What types of problems we solve, it really depends on what discipline of an engineer you're talking about. So for aerospace engineers, they design aircraft, spacecraft related systems and the associated equipment. So aeronautical is one branch of aerospace engineering, which refers to the design of systems that are flying within the atmosphere. And then astronautical engineering refers to the design of systems that fly outside of the atmosphere. In other words, spacecraft. Chemical engineering is a field that applies chemistry, physics, and biology for the purposes of refining raw materials, developing processes to mix and produce chemicals that make valuable products like fuels, biomolecules, etc. In civil engineering, the main task is to design public infrastructure such as roads, railways, bridges, dams, building structures, as well as residential facilities. Electrical engineers design systems like circuits, electromagnetic systems. They also design computers, microchips. So computer engineering is a branch within electrical engineering. And then other electrical engineers design telecommunication systems, like cell phone networks, for example. The field of environmental engineering is associated with the design of solutions for environmental problems, really what we're studying in this class. And so that includes the design of water supply, wastewater treatment, solid waste management, recycling systems, soil remediation to clean up contaminated sites, and air pollution prevention and control systems. And then finally, mechanical engineering, perhaps one of the most diverse fields of engineering, pretty much involves the design of any mechanical or thermal product like sensors, machines, devices like engines, turbines, refrigerators, elevators, conveyor systems, and even into the medical field with some crossover in biomedical engineering, the design of medical devices. So as you can see, engineers solve a very broad range of problems, and we organize their disciplines based on the types of problems that they solve. Here's an example of why designing appropriate solutions to environmental problems is so important. So when I was a recent graduate of civil and environmental engineering, I participated in a study with a nonprofit organization called Water for People, where the task was to develop an assessment of water and sanitation solutions that had been provided in a particular region of Bolivia where this nonprofit organization was doing some work. So water and sanitation systems involve drinking water and also toilet systems, right? Like management of human waste and provision of drinking water. And one problem that we see when engineered systems are designed to be perhaps technically correct, but not appropriate for the setting, is that they fail. So here's an example of a community where I worked with this organization, and we noticed it was a school that had 4 different toilets that were each constructed by different organizations with different funding sources at different periods of time. So toilet number 1 was designed by organization number 1 with funding source number 1, and it appeared to be a well-designed toilet, but it eventually filled up with with fecal sludge, and there was no resources at this school to be able to empty the toilet and allow it to be continuously reused. So the solution was that they closed the toilet and found eventually funding for constructing a new one. So new toilet number 2 came around, very similar problem with a different design. Eventually the toilet got clogged. There was no availability for resources for maintaining the toilet, so new toilet number 3 was constructed, and eventually new toilet number 4. So what happened here is that we have an issue of toilets that were designed according to some guidelines, sized, with the capacity according to the population in the school, but they were not taking into account the appropriateness of the technology and the availability of resources in this community to operate and maintain the designs that were chosen. So this is a quote that comes from a textbook in environmental engineering. Basically says, despite the great promise of engineering to solve the world's problems, the world is littered with broken down pieces of infrastructure like wells and unused latrines. Furthermore, engineering structures like dams, hydroelectric dams, have displaced hundreds of thousands of people, causing extreme problems related to the environment and people's well-being. So while these projects may have been constructed with the best of intentions, as it's said in this book here by Dr. Mihalcik, they often fail or they have devastating societal effects. So why am I telling this story? Because if we use the engineering design process correctly, we can avoid some of these societal failures. All right, and so what's the engineering design process all about? Well, it's actually pretty similar to a method that you've probably studied in a previous class called the scientific method. All right, and so I'm going to draw some analogies to why the engineering design process is similar to the scientific method and how it's different from the scientific method. All right, so in the scientific method, the first step is that you develop a new question, a new research question. Why does this happen? Or, what is the cause of this phenomenon, right? The second step in the scientific method is to consult the scientific literature. So you start reading articles about what have other people found about this issue, about this question that I have. Step number 3 is to formulate a hypothesis. After reading the literature, after thinking about the question, you come up with a hypothesis. I think this is happening because this, right? Then the next step is to test your hypothesis through experimentation, right? So is this really the cause of why this other thing is happening? Let's test it, right? Then we collect data, we analyze the data and draw conclusions, which lead us to either accept or reject our original hypothesis. All right, so this should look familiar. This is the scientific method, and the engineering design approach has some similarities to the scientific method, but it also has some key differences. All right, and you'll notice in the scientific method that after you accept or reject your hypothesis, it often leads to a new research question, or you might revise your original research question. So now let's talk about the design thinking process. All right, so the engineering design process. Step 1 of design thinking is to empathize. This is something that engineers, perhaps a long time ago or a while back when engineers were trained, didn't think about this step too much, right? But empathizing as the first step to designing a product is extremely important. It means that we need to learn about the people for whom we are designing by observing, by listening, and by engaging in conversations and discussions. This allows us to define a more appropriate and, importantly, a human-centered problem statement based on that empathizing phase. Right, so we're able to define a problem statement that really captures the problem from the people's perspective, the people who are designing the system for. All right, and in that process, we can also identify some important criteria for design and some important constraints for design. Step number 3 of design thinking is to ideate, meaning to develop new and unique ideas for alternative solutions that can address the problem that was defined in step 2. Once we have ideas, we might start to develop a prototype, right? Prototype is an inexpensive, scaled down version of the proposed solution. Now there's an iteration process that happens here, where after the prototype is designed, developed, you will seek feedback from the design population, from the population of people who might use this product, and then iterate based on feedback to improve the solution. Based on what you learned in step 1 of the design thinking process, that information will go into choosing the most appropriate solution. So that's why during the ideation phase, it's very important to identify not just one, but multiple alternative solutions that can solve the problem at hand. That way, you can really learn from the design population to develop the most appropriate solution that solves the problem and is also going to be sustainable. Step 5 is to test. So here we test the best solutions that were identified during the prototyping phase, and we do this iteratively until we finally have a solution that is going to be marketable, that's going to serve the population in need of a design solution, and that's going to be, sustainable in the long term. And if the prototype fails, right, before testing, we need to reassess and we might even need to re-evaluate our problem definition. Maybe we weren't defining the problem the right way, as was in the case of the 4 toilets at the school in Bolivia. Maybe the problem was not being defined the correct way, and therefore the solution wasn't the appropriate one. So let's first, before we get into step 1, let's talk about how this is different and how this is similar to the scientific method. Right, so developing a new research question is similar to defining a problem statement. Right? Ideating or coming up with alternative solutions to a problem is fairly similar to formulating a hypothesis. Right? Thinking about what might be the answer to the question or what might be the solution to the problem. Then testing the hypothesis and analyzing the data can be seen as analogous to prototyping and testing, right? It's an iterative process. We might go back to the drawing board during this process, revise some aspects of our design, of our prototype, and if the prototype fails, we might go back to some of the initial stages. We might start to empathize in a different way or learn more about our design population. We might redefine the problem statement. Just like with the scientific method, after accepting or rejecting your hypothesis, you might go back and revise your research question, revise your study design, and start the whole process over again. Right, so how is it different? Well, the design thinking process is definitely more applied. It's more applied to a specific problem, whereas the scientific method is often applied to some theoretical question or some scientific theory. But you can see some of the analogies, some of the differences between the scientific method and the design thinking process. So now let's start to get a little bit more in depth on each of the steps. How do we complete each of the steps of the design thinking process? Right, so step 1 is to empathize, right? And the objective here is to learn about the people for whom you are designing by observing, listening, and engaging. All right, so I have a quote up here by Maya Angelou. She said, people will forget what you said, people will forget what you did, but people will never forget how you made them feel. All right, and by identifying with a person's feelings, by you know, engaging with them on a deeper level, you can really understand what is the problem that's being experienced, and what are the causes of the problem, and what are some appropriate solutions to that problem. All right, so you want to think about, you know, what are people saying? Direct quotes based on things that you may have heard people say. For example, if you conduct some interviews with stakeholders from your design population. So, you know, let's take the example of a water system that's producing water that may not be safe. You know, like was the case with in many cities that have experienced lead contamination in their water sources. Or, you know, the choice to use bottled water over tap water. All right, so maybe you hear people saying things like, well, kids like the taste of bottled water better than they like the taste of tap water. All right, so what next step is, what might people be thinking? You know, consider what people might be thinking, but they may not be explicitly revealing these thoughts. For example, if they say something, it might lead you to believe that they don't believe that the tap water is safe to drink. Right? If they say, they give you hints that you know, they're hesitant to trust the tap water. You know, there's maybe they talk about some situation in a different community where the tap water was found to be unsafe. All right, and that might be something that they're thinking, something that they're feeling. Pay attention to what people are doing. So look at concrete actions that people appear to be taking. For example, if you're doing a community assessment and you notice that there's a direct pipe leading from some surface water over to a pool, even though a person might be saying that they only use water for irrigation, you might be observing something that implies that they might also be using the water for recreation. So it may have not occurred to the person in an interview to say, or they may be embarrassed to reveal certain activities or certain actions, but perhaps there are actions that are being taken that are not revealed through what people are saying, but observations can give you some hints as to what might really be the situation. And oftentimes I think people may not share certain things because of a lack of trust. Especially if you're an outsider from a community, you know, a lack of trust. If you're from a company, there may be mistrust of a company, of private sector companies, mistrust even of the government if you're coming from a government organization. So you got to know, you know, what the feelings are of the people in the community where you're working, and pay attention not just to what people are saying, not just to what people might be thinking, but what do you notice people are doing? And then finally, the last one, you know, what might people be feeling? And this is the one that can be the most difficult to get at. It might require an extended amount of time of getting to know people and observing, listening, and engaging, right? So, you know, maybe people are feeling frustrated about something with their government, with their local government, right? Maybe they're frustrated that one problem is being addressed, but not another. Maybe they're frustrated and they feel that they're being left out in a certain aspect. So you want to pay attention again during the empathizing phase on what people are saying, what people might be thinking, what you see them doing, and how they might be feeling. And on this note too, I want to talk a little bit about community-based participatory design. So community-based participatory design is an approach that specifically requires the involvement of the design population in design decisions. Now, this is not always done with engineering projects, but especially when it comes to public projects, public infrastructure projects, for example, and a lot of environmental solutions to environmental problems, right? These types of projects often require a large degree of input from the community that's going to be using the project in order for the project itself to be sustainable. This is that aspect of social sustainability, which is one of the 3 pillars of sustainability: environmental, economic, and social. So these typologies can be used to describe the level of community input into the design process, into the design thinking process, right? So we have here at the top passive participation, which is very low input from the community. In this type of project, people from a community might be told by the design team what is going to happen, or maybe even something that's already happened. But no one on the design team necessarily listens to or pays attention to people's thoughts or responses, right? So there is communication happening, but it's a one-directional communication. It's happening from the design team to the community, and there's no opportunity for input or for interaction. Information giving is fairly similar. In this typology, people from the community may participate perhaps by answering questions through surveys or questionnaires. So they don't necessarily have the opportunity to influence the design process, although they are sharing information that may be used by the design team to determine what it is that's going to happen. There's also participation by consultation. So this is a little bit more community involvement than the first two typologies. Here, people from the community participate by being consulted. So the design team starts listening to people's views to define the problem and the solutions. However, they don't necessarily concede any of the decision-making power, right? And the design team doesn't necessarily feel any obligation to incorporate people's views into the final design, right? So participation by consultation still lacks some ability of the community to influence what decisions are being made. Participation for material benefits can be described as a situation where people from the community participate by providing resources, for example, like labor or operation maintenance, in return for incentives. Right? So maybe there is some incentive that's given by a local government for the community to participate in some way or to provide resources in some way. However, with this typology, people have no stake in, they don't necessarily have a stake in prolonging the activities once these incentives go away. All right, and the incentives can be, monetary incentives or other types of incentives that are non-monetary. The next typology here is functional participation. So here, people from the community participate through groups that might be formed by the design team to meet predetermined objectives that are related to the project. However, so that their involvement in the design might be more involved than these first four typologies, might be more detailed than the first four typologies, but this involvement doesn't necessarily happen at the early stages of design cycle, right? So maybe some major decisions have already been made, but the groups nevertheless are influencing how the design is going to be implemented and influencing some decisions that are made, right? So the design group is ceding some of that decision-making power to the community, and these groups may eventually become self-dependent, right? Unlike the participation for material benefits typology, where they tend to go away after incentives go away. The next typology is called interactive participation. This is one of the most involved community-based design typologies, right? So people from the community participate in a joint analysis with the design team, which leads to action plans, formation of new groups, or maybe the strengthening of existing ones. This involves interdisciplinary methodologies, right, to make use of systematic and structured learning processes. Groups are taking control. People are taking control and ownership over the decisions, even from an early stage in the design process. And therefore, they're given the power to decide what happens, and they also have a stake in maintaining and operating the design product and service, which will lead to higher impact and better sustainability of the design. And the highest typology in terms of the most extensive community participation in the design is called self-mobilization. So this would be the scenario where people from the community participate by taking initiatives that might even be independent of the external design team to develop a solution. So the self-initiated mobilization and collective action may or may not even challenge existing inequities in the distribution of wealth and power. Right, so this is kind of really a self-mobilized, self-initiated intervention that happens from the community and challenges some existing structures and distributions of wealth and power. All right, it's more of a grassroots type design process. So you have it is, 7 typologies of community-based participatory design, and the top one here being the least amount of participation from the community, and the bottom one here being the most amount of participation from the community. In general, for social sustainability of engineering projects, it's generally better to be on the higher end of this typology, right? Interactive participation, self-mobilization, functional participation, right? Involving community members throughout the design process. All right, so after step 1 of the design process, where we empathize, the next step is to define the problem, right? Come up with a human-centered problem statement that's based on what you learned during the empathizing phase. And to help you think about important aspects of your solution, like the who, the what, the why of your solution, I'm going to provide you with the following template, right, which helps you produce a draft problem statement before you actually start thinking about a potential solution to the problem. All right, so this statement goes like this: blank needs a way to blank so that blank, right? So the first blank is who. Who is it that might be needing to use your solution? Who is your design population? And who are the stakeholders involved? They need a way to do what? What is it that needs to be done? What's really the root of the problem? What needs to be solved? So that, and then this one addresses why. What is the final outcome? What's the desired outcome look like? What does success look like for this design? All right. So let's look at an example. Let's suppose we have a situation at this is a refugee camp, like a very large refugee camp, where the population density has become quite large, and to accommodate water and sanitation needs in this refugee camp, pit latrines were installed, and groundwater systems were installed to pump groundwater from the aquifer. All right, so pit latrine is a type of toilet that looks like kind of like this. Can have different construction materials, different roof materials, different door materials, but basically inside is a toilet with a pit that's dug into the ground, and the excreta goes into the pit, and when the pit fills up, either the pit is closed and a new one is excavated, or the contents of the pit are emptied and transported over to a central treatment facility. All right, and here's a problem definition, problem statement for this situation. Let's say the United Nations Refugee Agency and their partner organizations need a way to build fast, cost-effective, and culturally appropriate toilets and fecal sludge treatment systems in refugee camps, perhaps refugee camps with high population densities, so that groundwater aquifers do not get contaminated. All right, so this is a very detailed problem statement that has the who, very specific who, the United Nations Refugee Agency and their partner organizations, that is the who. And they need a way to do what? They need a way to build fast, cost-effective, and culturally appropriate toilets and fecal sludge treatment systems, right? And why? What is the outcome? So that groundwater aquifers do not get contaminated. All right. So how might you arrive at developing a problem statement like this? One strategy that you can use is something called the 5 whys technique. All right, if any of you have children, or if you have cousins or younger siblings, you know that when kids go through the age of like 2 or 3, they enter that why phase where they ask why. Every question is why. All right, so that's basically what this technique is all about. It's force yourself to ask the question why as many as 5 times, and your goal is to really drive down to the root cause of the problem. So this technique might be effectively used in groups, in a group discussion. So let's say you start with a first draft of your problem statement. For example, people are not drinking the tap water. Right? That's an example of a problem statement. Another statement related to the previous slide that we saw: people at refugee camps are getting sick from the drinking water. Right? So you might think that that's the problem. That's the problem statement. But when you start asking yourself why, you can drive down and get a little bit more detailed. For example, all right, people at refugee camps are getting sick from drinking water. Why? Well, they have stomach illnesses, and fecal bacteria are being detected more frequently in the groundwater, especially now that the camp is getting larger and the population density is increasing. Well, why? Why are they getting stomach illnesses? Why are we detecting fecal bacteria? Well, toilets are being used in the camp. They're waterless pit latrines, and it's possible that they might be leaching the bacteria into the surrounding soil, where they might get into the aquifer, which is used by the residents as a source of drinking water. So that could be the reason why people are getting sick from the drinking water. Okay. Again, why? Why are people using waterless pit latrines? Well, the residents are using pit latrines because that's the form of sanitation used in their hometowns. It was also the quickest form of sanitation that the organization was able to construct in the camp. And maybe the camp also started out with a lower population density, and then the crisis grew, and so population density increased. But yeah, that's why they're using the pit latrines. So that's an important aspect, is that this is the form of sanitation that maybe was used in their hometowns. Next, why? Why? Well, residents were used to living in rural areas where they had lower population densities. Where they came from, the use of pit latrines didn't contaminate water sources, so it was never an issue before, right? And with all that information, after going through, in this case, 4 whys, you might come up with that revised statement. The UN Refugee Agency and their partners need a way to build fast, cost-effective, and culturally appropriate toilets and fecal sludge treatment systems in the camps so that groundwater aquifers do not get contaminated. All right, and so it's important to note this 5 whys technique. 5 whys is kind of a guide, but you might be able to reach the root cause of the issue, in 3 or 4 whys, or maybe it takes a little bit more. It really depends. Let's look at another example. All right, microplastic beads are contaminating the ocean. All right, and this is actually one of the videos that you'll watch for your first assignment, where you have the option of watching one of 3 videos, and you can take this original statement and drill down to a more detailed problem statement. Okay, so once we've empathized and defined our problem statement, perhaps using the 5 whys technique to drill down to really what is the root cause of the problem, and come up with a very detailed problem statement, we need to identify criteria and constraints. And this is another input that comes from the empathizing phase, right? So in a real project, there would be extensive discussions with community stakeholders and project stakeholders about, what are some of the constraints for design? What are some of the criteria? A lot of times the criteria for design might come from local jurisdiction, like local regulations, laws, and those have to be taken into account when coming up with the design. right? And that's part of the job of engineers is identifying these criteria and also identifying the constraints, and then coming up with a design solution that fits the need, right? So the criteria for a project refers to the requirements that a solution needs in order to be successful, right? So you think about the purpose of a solution. You know, what is the purpose of the solution? How many people should it serve? You know, so if we're designing like an electrical system, what's the power requirements? How many people are going to be using the system? What's the required capacity? Often these are questions of things like power, strength, volume, flow rate, right? Other questions related to criteria are like, what do you want the solution to do? You know, what does it need to be able to do? And what does it need to do in order to be successful? Constraints, on the other hand, tend to be related to limitations for a solution. And the most common examples of design constraints are things like available funding, the types of materials that can be used, time constraints, constraints related to human resources, the availability of human resources or the availability of trained labor and human resources. And there's others as well, right? So you want to think about things like, what are your limitations with this design? Does the solution really need to be inexpensive in order to meet the need? Does it need to use specific materials? Like, for example, do the materials need to be something that's easily found in the local economy? Right? If something breaks down and the material needed to replace the item that broke has to be imported or is very expensive because it comes from you know, some location very far away, then that might be a constraint for design in a particular region, right? And sustainability might impose some constraints as well. So maybe there are constraints related to the amount of emissions that a particular design can contribute to, right? So you have to constrain the design in order to meet the design criteria and to satisfy any constraints. Another way to conceptualize this is that a criterion is a standard or an attribute of a design that can be measured. And the measurability of a criteria ends up being pretty important. So you want to think about, you know, this design needs to be like this, or it needs to have this, or it needs to have so much of this, or it needs to produce so much of this, you know, a certain amount that can be measured. Constraint is a limitation, a restriction, or a condition that must be satisfied by a design, right? So some examples of language that are used in constraint statements are like, this design can't have this, it can't be like this, you know, it has to be this other way. A few years back, probably about almost a decade ago, actually, the Bill and Melinda Gates Foundation started an initiative, a project called the Reinvent the Toilet Challenge. So this was a project where this organization provided funding to universities, scientists, companies, researchers from around the world that were interested in coming up with alternative design solutions for the toilet, basically inventing a new product that can substitute the toilet and meet the need of sanitation in many areas of the world where toilets are not accessible. You know, so there's billions of people in the world that don't have access to safe sanitation. You know, they don't have access to safe toilets. And so this challenge here was constructed in order to try to find a solution to that environmental and public health problem. So the problem statement for this Reinvent the Toilet Challenge was like you can see here. People in the world without access to safe sanitation need a way to buy or build a better non-sewered toilet to prevent the transmission of diseases, right? So see, again, in that problem statement, you can see the who, you can see the what do they need a way to do what? and you can see the why, you know, what's the desired outcome? Prevent the transmission of diseases. So here's a list of design criteria and constraints. The toilet must remove germs from human waste and recover valuable resources such as energy, clean water, and nutrients. Right, so these design criteria and constraints were posed as part of the Reinvent the Toilet Challenge. The toilet must operate off the grid without connections to water, sewer, or electricity. The toilet must cost less than 5 cents per user per day. The toilet must promote sustainable and financially profitable sanitation services and businesses that can operate in poor urban areas. And finally, the toilet must be a truly aspirational next generation product that everyone will want to use, both in developed nations and also developing nations. All right, so these design criteria and constraints were really constructed by the Gates Foundation in order to make sure that the design solution being provided by teams was addressing the needs, was addressing the criteria, and was considering the constraints for the population in the world that lacks access to safe sanitation. Right, their constraints and their criteria are very unique. They're very specific. They're also can vary greatly from one region to another, but relative to, let's say, the population in cities in the United States where sanitation coverage, wastewater treatment tends to be very high, the criteria and the constraints for designing toilets in low-income, poor urban areas of developing nations were different. And so that's what this Reinvent the Toilet Challenge came up with, this problem statement and these design criteria and constraints. So which one of these are criteria and which one are constraints? So these are more consistent with language that would be described as criteria, right? Criteria that the toilet must remove germs from human waste, right? That's a basic functionality of a toilet, is it must prevent the transmission of diseases that are transmitted through human waste. Another criteria that it has to recover valuable resources like energy, water, and nutrients. That's kind of like a sustainability criteria. The next one, it must promote sustainable and financially profitable sanitation businesses and services, right? And that's really another sustainability criteria. It needs to be economically sustainable so that local businesses and services can operate in a financially profitable way. And then the last one, the toilet must be aspirational, next generation product that everyone wants to use. So it has to be something that's a product that's desirable. These two right here are more consistent with constraints, right? It must operate off the grid because a lot of the population in the world lacks access to water, sanitary sewer, pipes, and electricity. So we need a toilet that can serve the needs and satisfy the design criteria with this particular constraint. And the other constraint, because it's for low-income areas, it needs to cost less than $0.05 or 5 cents per user per day. Here's one example of a group that developed a solution to that problem statement through the Reinvent the Toilet Challenge. Right, so the blue Diversion autarky toilet for sanitation off the grid was developed by a group at an organization called EVAG. And how does this system work? It's essentially a standalone toilet that recovers energy, nutrients, and water from the waste, and has hand washing facility. It satisfies the design criteria. It operates off grid, with a solar panel. And as you can see here, it's got multiple levels, multiple layers. The design, has a user interface where the user uses the squat style toilet. There's a hand washing station right behind the toilet. In the underneath compartments, you have one region where fresh urine is separated out from feces and stabilized. using hydrated lime. This preserves the urea, which is a nitrogen containing compound in the urine, and it also serves to kill off any viruses or bacteria that might be in the urine, so that the urea, the nutrients, the phosphorus, the nitrogen, potassium in the urine can be recovered as fertilizer. This compartment down here captures the feces, which are separated from the urine, and through a thermal dewatering and drying process, excess water from the feces is evaporated off. And that allows the combustion of the dried feces to, which will incinerate and kill pathogens and allow the production of pellets that can be used as a fuel source. The evaporation of stabilized urine happens as well. So excess water is evaporated, dried nutrients are deposited onto a blotting paper that further contributes to the fertilizer that can be produced from this system. And you have the hand washing station, which recycles water and cleans the water in the process as it recycles. So, you know, this solution was the final product of years of developing design ideas and testing out and building prototypes and getting feedback from stakeholders. So, you know, that's where you get to the next phase, or you know, how do you get to a solution like that? Really, the next step of the design process is the ideation phase, right? So the blue diversion team, before developing that final solution that you saw there, first they went through quite a bit of brainstorming, ideation, where they identified alternatives and different types of solutions to the problem, and then, you know, workshop those solutions with stakeholders from the global community to eventually revise the prototype and come up with the version that you saw there. So how do we ideate? How do you come up with these ideas? There's some strategies that can be used. One strategy you might be familiar with already is called brainstorming. So here, a team of people meet to generate new ideas by removing inhibitions to enable free thinking, right? So the idea here, you generate as many spontaneous new ideas as possible. No idea is a bad idea. Every idea gets written down without any criticism. And only after the brainstorming session has ended do you go back and look through the ideas and start to critique and evaluate which ones might be better than others. All right, and a similar process is called the brainwriting method. So this is often referred to as well as the 6-3-5 approach. So here you can use up to 6 participants in a group. And each participant writes down 3 ideas on a worksheet within 5 minutes. So the idea is really just kind of like a brain dump, like get 3 ideas down on a piece of paper within 5 minutes. So inhibition free, come up with ideas. You have 6 participants, each writing 3 ideas. That quickly generates 18 design alternatives, 18 ideas that can then be revised, evaluated, right? And so the idea now is that you pass your piece of paper with your 3 ideas over to another participant in the group who will elaborate on those ideas. And then you'll receive the ideas from a different person, and you'll start to elaborate on their ideas. And you do that until all the ideas make their rounds. At the end of this process, you've got 18 ideas that have been reviewed by 6 people. Right, so that's brainwriting. That's another strategy that you can use in a group to identify new and unique alternative solutions to the problem statement. Another approach that's used in ideation, and I kind of like this approach, this is an interesting one, is that it's called the worst possible idea. Right, so this is a method that sort of flips brainstorming on its head. Instead of trying to find good ideas, which might create a sense of pressure, you know, you get blank thoughts, you don't know where to start, you're not really sure what makes a good idea. This approach starts off on the other end. You say, what's the worst possible idea that will definitely not work? And then you start to look at that idea, and the group starts to list the properties. You know, what are the properties? What are the reasons why this idea is so bad? And once you identify those properties that make a bad idea, you can start to look at, how to find the opposite of those bad attributes of the idea. And then think of a design solution that has the opposite of those bad attributes, right? So this can be an effective approach as well. And here you see again the evolution of that blue diversion toilet. It didn't start off with the way that you saw in the first photo. The first design idea looked very different, right? You had two separate products, a toilet and a hand washing station. In the design model, this was in 2011, design model developed in 2012, merged those two into a single platform. Prototype number one, added some features to that design platform, and it was field tested. After that field test, there were certain things discovered about the way that the system functioned, like the hydraulics of the toilet were ineffective in some aspects, or they were lacked some efficiency, so they had to be re-engineered. Eventually, it allowed the group to come to a smaller, more user-friendly interface with fewer moving parts. Like it used to have a foot pump, and they were able to take that out of the equation after the revised design was prototyped in 2014. So you could see over the course of 3 years how this one design idea has been prototyped, field tested, revised, prototyped again. And that's what step 4 in the design process is all about. Prototype is to produce an inexpensive, scaled down version of the proposed solution. Here's another example. This is an organization called Potters for Peace, which back in the 80s came up with a prototype for developing a filter, an inexpensive filter for drinking water that would remove certain contaminants, right? Contaminants like pathogens and other dissolved constituents in water that can make people sick. So, they developed prototypes of this filter. The filter was based on a ceramic pot design, a ceramic filter that allowed water to pass through, but certain contaminants were withheld by the ceramic filter. They prototyped that ceramic filter, figured out, how can it be made easily with local resources, local labor, in settings where there's no electricity. How does the design need to change in order to adapt to local production facilities and the ability to make these things on a large scale? They eventually added things like a silver lining on the inside of the ceramic filter, which provided extra disinfection capability for pathogens like viruses that were able to make its way through the filter, but with the silver lining, they would get killed off in the process, right? And they eventually arrived at testing the solution and coming up with a final product, which was called Filtron, which has now been distributed and replicated in many different countries throughout the world, and is now a commercial product that you can find in many areas of the world for filtering water for the purposes of drinking. Right, and this whole product was, was developed through the design thinking process, ideation, coming up with ideas, using input from stakeholders, like the use of local materials, the use of local production facilities, and eventually arriving at a solution that made sense and was economically profitable for the design population, right, for the stakeholders. All right, so there it is in summary, the design thinking process: empathize, define, ideate, prototype, and test. And then notice that there's lots of iterations here, right? So go back to the drawing board if your test doesn't work, get feedback, revise your prototype until you arrive at a solution that meets your design criteria and constraints.